Welcome everybody, this is lecture 12, the uniform distribution. So since our variable is continuous, we focus on an interval of values rather than a specific value, and we want to calculate the probability of my x, the random variable, to be inside a specific interval of values. And we are gonna use, of course, the probability density function, BDF for short, and give me the probability as an area under the curve. So probability of x to be inside a specific interval of values is nothing but the area under the curve for that density function or BTF, and because of that we are gonna end up with that fact that the probability of any continuous random variable to be exactly a specific value is nothing but 0, because there is no area for a specific value. Areas are just for intervals. So what are the properties of the BDF, the probability density function of a continuous random variable? That we are gonna call it f of x, the BDF is f of x, so the f of x, the calculated probability is greater than or equal to 0, and the total area under the curve of the BDF is gonna be equal to 1, and this is matching what we had learned till now for any probability mass function. How to calculate the probability now for x inside any specific range? We are gonna see that in a minute, or in a second actually, but let me just say that the probability of my x to be inside the interval from C to D, not including C and D, is exactly equal to the probability of x inside the closed interval C and D, and this stems from the fact that probability of x equal a specific value, so this equal to signs is equal to 0, so it does not matter whether we write it or not. Now let me see some examples of the shapes of BDFs. This is a BDF, which we're gonna know later. This is a normal BDF, and as you see, it's like an upside down pill. Here, the probability of x inside that interval from 1 to 2 is exactly equal to the area under the curve from 1 to 2, where this curve is the whole curve or the BDF for the x for this specific distribution. Another example here is that one. I could have one of the BDFs. This is an example for another BDF, not the normal. And here, if you want to calculate the probability of your random variable x that is following this specific BDF, the exponential function, this is exactly equal to the area under the curve on that interval from 2 to 4. And the last image that we are gonna see today is the BDF, and this BDF, as you see, is nothing but a rectangle. And if you want to calculate the probability of your random variable x to be defined or inside a specific interval from 3 to 6, this is nothing but the area underneath again the whole curve from 3 to 6. And another note here, the total area for that f of x is which is defined here from 2 to 9. This is the total range, so the total area for the whole rectangle is exactly equal to 1. And similarly here for that curve, the total area from minus infinity to infinity under the curve again is equal to 1, while here from 0 till infinity, that whole area is again 1. So this is normal distribution, this exponential function distribution, or the exponential distribution function, and this is actually what we're gonna focus on today, the uniform distribution, or specifically the continuous uniform distribution. So the simplest continuous distribution is the uniform distribution, and here we will find out that my random variable x that is distributed as a continuous uniform distribution is having equal density across that interval a to b. So x is inside a to b is having the same equal probability for any intervals of same length. We are gonna end up with the same probability. And notation wise, we are gonna say x is following uniform UNIF on the range from a to b. The formula for this distribution is as such. It's f of x, your density function for your uniform random variable x is 1 over b minus a, where x is defined to be again between a and b. If x is less than a or greater than b, we are gonna have a 0 for f of x. And as you see here, your f of x is constant. 1 over b minus a does not change by the change of x, which means it's constant all over that interval from a to b, and again 0 outside. So let us see the graph. So here is my graph. X is from a to b. From a to b, the density f of x is gonna have the height of 1 over b minus a, which is that value. So this is the uniform distribution. Beyond that range, you are gonna see that the probability, or my f of x, is equal to 0 or defined to be 0 if it is less than a and greater than b. So this is the curve of the uniform distribution, where we did see before it was just a rectangle, because we are saying, okay, we are gonna focus on that one, and implicitly beyond that range you are gonna have 0 probability, as our curve is saying here, or showing here. Now, what is the mean and variance, or mu, sigma square, and even the standard deviation sigma? It's defined to be mu is the midpoint of the interval of your x. So if x is between a and b, the midpoint is a plus b over 2, which is the mid range of my variable x. So this is your mu, the mean, while x is sigma square is defined to be that formula, which is saying the length of your interval squared over 12, and as usual the standard deviation, or the sigma, is the square root of my variance. So these are the fingerprints of the uniform distribution, and let us see how to calculate the probability for x to be in any interval. So we are gonna use the principle of an area. As we see now, if you want to calculate the probability of your random variable x to be between c and d, this is exactly equal to the base times the height. So here is again our uniform distribution. This is for a uniform random variable, of course. We are still talking about the uniform distribution. So because the uniform distribution is after all a rectangle, if you want to find the probability of x in between c and d, well, imagine with me, this is c and this is d, so you want to find the probability of x in between these two green lines exactly, okay? Because the height of that rectangle between c and d, this is the height, okay, while the base is that part, which is d minus c. So to find the probability of x in between this interval, or inside this interval, you are gonna calculate it as an area of a rectangle with a base equal to d minus c times the height, and the height is 1 over b minus a, which is the probability density function for a uniform distribution. And as you see, we are gonna end up with that formula. So to calculate a probability for a continuous random variable c and d, all what you need to do is to calculate the interval length that you are interested in and divide it over the b minus A or the total interval, or in another word, if you're gonna look at it like 1 over the b minus a, this is the height of your rectangle. Again, this is a rectangle logic, and it works for x being inside that range a, b. If x is outside, as we said before, the probability or that height is gonna be exactly 0. So let us see one example here. The path wait times the amount of time in minutes that a person must wait for a pass is uniformly distributed between 0 and 20. What is the probability for that person waits more than 5 minutes? And if x is the waiting time, so what is the probability of x greater than 5? To see, this is the BTF between 0 and 20, and it is defined to be a uniform distribution, which is 1 over 20. Why? Because 1 over b minus a, which is 1 over 20 minus 0, which is 1 over 20. This is the height, and we want to calculate the probability of x greater than 5. If this is 5, then we want to find that area. That area is exactly equal to the area of this green rectangle, which is the length of the interval, which is 20 minus 5, over the total length from 0 to 20, or multiplied by the height again, and this is it, the solution for that one, 15 over 20. Another example, if x is uniform between 2 and 8, we want to find the probability of x to be between 3 and 5, and also to find the probability of x between 2 and 6.5, and the probability of x between 1 and 6.5, and find the mean and find the standard deviation. So what is a uniform distribution, or f of x, for that x that is following uniform 2 and 8? This is what? This is again 1 over b minus a. So we are gonna end up with 1 over 6. And again for x, if x was inside that interval. So that probability of x in this tiny little interval inside the whole interval here, it's according to our rules, it's the length of that interval, or the base of my rectangle. So 5 minus 3 is 2 over the total interval, or multiplied by the height. So it's what? It's 2 over 6, which is 1 over 3. How about that one? Here we want to find the probability for a little bit lengthier interval, x between 2 and 6.5. Again, that length is 6.5 minus 2, which is 4.5 over my 6, or the total length of my interval. This would be what? 4.5 over 6. So it's that one. Now, how to calculate that probability? Here we have to be careful. That interval is actually containing something which is outside, as we said, outside that range. The f of x is 0, total height is 0, so I need to partition my interval here into 2 areas, or into 2 probabilities, from 1 to exactly less than 2, plus another probability which is taking the 2 to 6.5. So partitioning my whole interval to 2 pieces, just because in that piece I am following that height, or the BTF is equal to 1 over 6. Outside that range it has to be 0. So that first part is 0 plus that probability, and this probability is nothing but what we had before, so we are gonna end up with 0.75 again, but just we got rid of that part. So the mean is the midpoint for that interval, so 8 plus 2, 10 over 2, 2 is 5. Again, the sigma square was defined to be the length of your total interval square over 12, and here we are just applying that rule. Okay, let me just try to write it. You remember we had that formula, sigma square equal to, we said b minus a, and this was our length of the interval square over 12. So applying that one, it's gonna give me 36 over 12, which is gonna be equal to 3, and because of that we had sigma square root of 3. So our new example is about round of error. The amount of sales tax paid on a purchase is rounded to the nearest cent. Assume that the round of error is uniformly distributed in the interval from minus 0.5 to 0.5 cent. What is the probability that the round of error exceeds 0.3 cent or is less than 0.3 cent? This means that I want the probability of the tails, or the tails being 0.3 in either direction. So it's like I want to calculate that probability. Probability of x is less than minus 0.3, okay, or greater than 0.3. So these are the tails. So if I have my, if this is the whole range of my uniform distribution, okay, this is the whole range, and I am interested to be, this is 0.3 and this is minus 0.3, and I am interested to be in that area exceeds 0.3 or less than minus 0.3. So we want to calculate these two areas, okay? So area, I can calculate the inside area and subtract it from 1, or I can calculate each one of them and multiply it by 2, because according to the area this one is exactly like that one. But what is the function here, the f of x? Let us see, the f of x is exactly equal to 1. Why is that? Because I applied the formula for the uniform distribution, which is saying 1 over b minus a. So 1 over b minus a will give me 1. So the probability of x to be between minus 3 and 3, it's 0.3 minus 0.3. So the length of that interval, it's 0.6. Okay, this is the length of that interval over the total length, which is that one minus that one, which is 1. So it's gonna be 0.6, and this is the probability to be inside these two limits from minus 0.3 to 0.3, which means beyond this or the other, the remaining area beyond the 0.3 from either direction is gonna be 1 minus 0.6, which is the 0.4. What is the mean? The mean again is the midpoint of that interval, or the mid-range for that one. This is b plus a over 2. 0.5 minus 0.5 over 2, it's gonna be 0. And this is normal or logic, because any round of error average should be 0. Sigma is what? Sigma is the square root of that length square over 12. So that length is what? Is 1. Square is 1 over 12. It would be 1 over 12. And for sigma, I am gonna put all of that underneath the square root. So it's gonna be 1 over the square root of 12. Now we want to calculate that probability, which is the probability of x between minus sigma and sigma, and this is actually, it's like finding the probability that the round of error, my x, will be within 1 standard deviation from the mean. Why? Because the mean is equal to 0. So x being between minus 6 sigma and sigma is like saying this is the probability of x to be within 1 standard deviation from the mean. And this is what? This is like the probability of the absolute value of x to be less than sigma, and sigma is here. So again, I'm gonna calculate that using the previous formula, which is the length of this interval, sigma minus sigma, which is gonna give me 2 sigma over the total length, which is 1. So that probability is actually 2 sigma. Now 2 sigma, which is equal to 2 over that 1, and gonna end up with that value 1 over the square root of 3. Our last example is find the value h that makes the function f of x a valid continuous probability distribution, and this is our graph for f of x. So I have here again a rectangle, and to let this be a probability density function for x, it means that that area has to be equal to 1, and this is similar to the PDF of a uniform distribution, so it's easy to calculate. And even if it wasn't, after all, a uniform distribution or a rectangle, you can also apply the same principle. The area under the given curve has to be 1, and if I know that part, the base, I can solve for h. So h here should be what? Let we do it together. H here times the base, which is, how much is the base again? It is 175 minus 50. So this is again the base, and this is the height. It has to be 1, which means h is equal to 1 over that difference. So if I'm multiplying that value, 1 over 25 by 125, it's gonna give me 1. So bingo, this is the value that will give you f of x, a valid f of x, as a PDF. And to wrap up everything, we say the continuous random variable, or the PDF for a continuous random variable, it's gonna calculate the probability as an area, not as points, because the probability of a continuous random variable to be exactly a specific point, a specific x is 0. We did discuss the uniform, and for the uniform we did see that it is a constant density. The height is the same all over the whole range of your x, and the probability is nothing but the rectangle area, and the mean is the midpoint or the mid-range. Spread depends on the interval width, because actually it's the sigma square is the length of our, or the width of our interval, square over 12, while sigma is the square root of that one. So this is the end of our lecture today, and thank you for being here, and see you next time.